Hello, I'm Sasha Kostovic. I'm the director of AA Labs, which is the research division of company Audio Analytic. As you know, sound recognition is very innovative technology involving artificial intelligence, and also involving, in order to get there, in order to make this kind of technology work, we need to do lots of research in the domain. There are several ways you can do research. You have empirical research, where you try to modify things until they start working. But you also have ways to do research which are more about modeling the structure and the interaction between various quantities and so on. And for that, there's a wonderful tool which is mathematics. Today we have the pleasure of welcoming one of the researchers who is really, really strong. I have a tremendous admiration for him. Really strong at modeling the acoustic phenomena, audio phenomena, with mathematics, with various forms of mathematics, and extracting new methods, new insight from very complex mathematical models. He's been one of the locomotives of sparsity and research in the sparsity methods, but you're going to see through his talk that his interest is much more varied than that. So please welcome Rémi Gribonval from INRIA in France.
Well, thank you very much, Sasha, for this very kind introduction. Today what I propose is to start with a brief, well, not so brief presentation of, some of the highlights of what is going on in the Panama team that I'm conducting in INRIA in the city of Rennes in Brittany. And afterwards, I'll give maybe a more focused presentation on some recent research on compression for large-scale machine learning. So let me begin with this overview of the activities in our team. As Sasha said, it's a team that's dedicated to mathematical audio signal processing. It ranges from the analysis and processing of audio signals to the design of new techniques for a massive dimension reduction in the context of signal processing and machine learning. So we're a team of about 20, including 4 permanent staff. So we've been working in the domain of mathematical audio signal processing for more than 15 years. And if you want to know more about the team, here's the address. The core expertise of the team, the core domain of applications in the team is definitely audio, from its capture to the analysis of its semantic content. But we also develop a number of mathematical tools that have applications much beyond audio. And so, for example, through collaborations, we've been investigating issues in underwater acoustics, in medical imaging, and more. So the scientific foundations of the team revolve around mathematics in high dimension, because we can represent audio signals and acoustic fields that are really high-dimensional vectors. Just as images and videos can be represented as vectors in high dimension. But more specifically for audio, we develop models based on geometric visions, probabilistic visions, and more. We design algorithms with a focus on computational efficiency and performance on particular tasks. And from the mathematical perspective, there's also the question of proving that these algorithms will actually perform well on the tasks. And of course, all this would not make sense, in particular in the field of audio, without designing proper experimental validation and reproducible schemes for reproducible research. Today, we're really facing new challenges revolving around the fact that acoustic data is becoming massive, both in terms of the amount of sensors that are deployed, but also the rates and the continuous flows of acoustic data that can be sensed. And these raise challenges that range from the variability, the huge variability of this type of data. Of course, what I've already mentioned, the volumes and the dimension that are to be considered, but also the variety of tasks that we may want to perform on this data. From entertainment purposes to monitoring and surveillance purposes, there's really a huge variety of tasks. So let me now try to give a more a view that's some kind of a geometric view that we develop, that we like to work with in the team and that we've historically worked with. It's the notion of many problems in audio and imaging in signal processing are from the family of inverse problems. Inverse problems revolve around the notion that there's something really huge, high-dimensional that is your object of interest, but you're only able to observe it partially. And from this partial observation, you need to retrieve the relevant information in your context. So you can think of sensing sound with only 2 microphones or 2 ears, while sound is a full acoustic field. It's an inverse problem to get back to the information, and you'll use models of simple generative models typically to do reconstruction. And a pictorial view here is that you'll hope that your observation is something which is low dimensional, your object is high dimensional. So without a model, there's many possible explanations for what you've observed. So historically, we've done a lot of work on designing or choosing low dimensional models, sparse models, and designing algorithms that exploit these models to retrieve a good estimate of your regional data. So this estimation will be good if your data fits your model well enough, and we will have, of course, if the model is not well adapted, you won't get much guarantees. A recent evolution, let's say in the last 4 or 5 years, the team has changed its emphasis. There's now a lot of emphasis on learning, and learning can occur at different stages. That can be about learning the model itself. So this is related to the notion of dictionary learning, non-negative matrix factorization, and more, where if you don't know in advance the model but have training data, you can try to infer the model to be reused at later stages in such inverse problems. This is also something that is developed at a higher level in music modeling. We are learning some motif structures, some models of recurring patterns in music. Something else that is related to learning is when the measurement process itself is not well known. There's some variability, channel variability, calibration issues in sensors. We have developed techniques reminiscent of dictionary learning that sort of calibrate the sensing device, exploiting the existence of a low-dimensional model. And you can also fit in there techniques for source localization to infer some kind of geometric information about the environment from the sensed acoustic data. And a last thing, and this will be the object of my detailed talk in a few minutes, is also the idea that in some cases you may want to design your measurement system so that it's massively dimension reducing while preserving the information of interest. This is more intended in the context where you want to control your computational resources or the cost of your sensing system so that you really reduce dimension but preserve information. So let me give a quick highlight on this dimension reduction aspects that I will develop further in a moment. So in terms of signal processing, there's the notion of compressive sensing, which is a technique for sensing high-dimensional objects with few resources. And this we have done in the context of near-field acoustic holography to design random antennas to perform acoustic imaging with 10 times less sensors or 10 times less recording time for the processing. But let me focus on some recent developments that have been undergoing in the with funding from the European Research Council with the notion of compressive sensing, compressive learning. So compressive learning is the idea is globally that when you do machine learning, you have to manipulate hopefully large training collections, which is an opportunity because a lot of information is present in this collection, but also a challenge because computing with large collections can be quite costly. An example is from a relatively old database. When you want to do large-scale speaker verification with Gaussian mixture models and universal background models, you need to learn a model. And you can use maybe the Mnist 2005 training set, which has 1,000 hours of speech. So that's a huge set. I mean, maybe today's standard is still not that huge, but compared to what we can do with compressive learning, which is reduce this to 4 kilobytes to a signature of 4 kilobytes with some techniques that I will develop a bit further. And from these 4 kilobytes, learn a GMM UBM model, which on a proof of concept performs better than what we can get with EM. The scales are completely different. So that's a result we're quite proud of, and I will detail a bit the underlying principles in a minute. Of course, don't hesitate to interrupt me at some stage in the presentation. Something else that I will also give a slightly more detailed overview in the longer part of the presentation is the idea that we can, in signal processing and machine learning, we manipulate matrices, and we manipulate huge matrices a lot. Huge, dense matrices are complex to work with, and when fast transforms are available, life is much easier. We all know the Fourier transform, which is associated to a fast transform, but there are many cases where we don't know whether a fast transform exists. And what has been developed during the PhD of Luc Lemagouarou is a technique to approximate a given dense matrix as the product of a few sparse matrices. This has enabled compression, compressed representations first, and accelerated computations. And here is an example on a matrix that arises in the context of brain imaging, electroencephalography. This matrix, there's a standard way of approximating it with the various levels of complexity, which is the SVD. So if you truncate the SVD, you get a poor approximation. If you keep the SVD, you get a good approximation. Well, with this type of factorization, we were able to get this type of trade-offs between approximation and complexity of the description of the matrix, or complexity and multiplication by the matrix. So the interest of this type of technique is that it's a data-driven technique where you can use it, for example, to learn a fast dictionary that can be reused once learned using fast computations. On this brain imaging setting, for example, we get an 80% speed up of computations. And it also means that since there's fewer parameters to describe your dense matrix than the actual set of all coefficients, from a statistical perspective, you can train it, you can learn it with fewer training samples. So sort of small data rather than big data setting where you can still infer with a more limited number of training samples. And we are currently working, we have a first version of an open source C++ library to exploit these techniques. So there's a historical activity in the team, which is audio source separation and localization. And this here is just a diagram to illustrate the philosophy and the status of this work. So there's academic work proposing new models and new techniques for source separation. This fuels the development of a flexible audio source separation toolbox which is jointly developed with Emmanuel Vincent from the multi-speech team at INRIA in Nancy. And this also fuels industrial collaborations with a number of patents and joint research projects. So to continue this overview, we've developed the notion of Cospar City, which is a twin of classical sparsity. In the PhD of Sergeant Kitic, we were able to develop this notion where, in a way, as an example for source localization in a complex but known acoustic environment, we were able to show that Cospar City allows to directly leverage the physics, the wave equation, and to merge physics with sparsity corresponding to the fact that there are few sources. We're able to develop a technique to locate the sources behind the wall, at least behind the door, let's say. There's some acoustic communication between two parts of a room. And also to show that with the Cospar technique, there's a surprising behavior, something that is surprising at first, is that the more microphones you get, the less it costs to actually get the localization compared to traditional synthesis frameworks where more microphones means more cost. I won't detail, but we've also shown that it's possible to use this in sort of joint or blind calibration settings. For example, if you don't know exactly the microphone characteristics, but you know that where your sensing has some form of sparsity, you can exploit it to calibrate the gains of the microphones in some settings. And we've also experimented for the moment on toy simulated problems the ability to infer the geometry of the acoustic environment or the impedance of the boundaries. So these are characteristics that can be helpful to solve the reverberation problems and more. We also used it for audio desaturation with real-time and online demos. Maybe I'll make them a bit later if you're interested, so that we have time for the detailed presentation. Maybe we can just hear one example. Here it's so this is a saturated sound, and this is desaturation. Okay, so to conclude on the activities of the group, I've put a highlight on some of the activities that may be most connected to today's meeting with you. There's also some growing activity on the notion of graph signal processing, where you have data that is structured not as time series, not as grids of pixels, but have more irregular structure captured by a graph. And there's the possibility of extending a number of tools from classical signal processing in this context. I already mentioned motif discovery in audio data and music structure modeling, which are two other important aspects of the activities of the group. And finally, because we believe that science is something that needs popularizing and needs to attract, we need to attract people in these careers, we've organized for the 7th year in a row Science and Music Days in the lab. The last edition attracted more than 800 participants. So with various conferences on audio signal processing, music modeling, and various types of workshops where people hands-on can test recent technologies. Okay, so this is going to be, let's say, a bit more technical presentation, but hopefully not too technical, but giving the ideas that have been developed in the context of an ERC project called Projections, Learning, and Sparsity for Efficient Data Processing. And so here what I'm going to try is to give you an overview of a combination of ideas that I've already mentioned, compressive learning and learn fast transforms, to do some sort of resource-efficient learning in a large-scale context. So okay, just to be on the same ground, what do I mean by machine learning here? Vaguely is the idea that you have a data collection, and from this data collection, you want to infer some parameters, parameters of a model, or parameters of a classifier, parameters of a tool that we'll use to perform some task. Classification, the dimension reduction, regression, recognition. So it really starts with a large training collection, and you can think of your own domain for the nature of the collection. And now there's a task that you want to perform. And from a mathematical perspective, you can formulate this task very often, maybe estimating a subspace for principal component analysis, finding the centers of clusters for unsupervised clustering. Maybe for dictionary learning, there's the notion of finding unions of subspaces with particular structures, or for classification, finding a parametric boundary between classes. So the starting point is your collection. You have a collection of training vectors. Each column here may be a set of MFCC coefficients or some feature descriptor of some audio frame or some image. You have this is large now in the large scale in the sense there are two senses, two meanings of large scale. There's the fact that these features could be high dimensional. If each feature is already an audio recording of an acoustic field with many microphones, that can be high dimensional. But there's also the idea that when we like to work with large collections because they carry relevant information and they are an opportunity. So these combined raise a number of challenges. And one of the questions we wanted to address in this project was to what extent and what tools do we have to compress the collection without losing the relevant information that is needed for learning. So we'd like somehow to have a simple way of compressing before even starting to learn. So there are essentially three routes to large-scale learning that I can see at this stage. So it's a course overview, but the first route is dimension reduction, where each feature is compressed to a lower dimensional feature. It's good to handle the large dimensional setting, but it does not necessarily cope with the fact that you may have very large collections. So to handle these aspects, there's a family of techniques that are based on some sort of smart subsampling of your data collection. So you could randomly subsample to decrease the size, or you could use maybe Nystrom method or corset techniques that try to pick representative samples. And then the goal is to have a not too costly technique to subsample and to ensure that the information will still be there. What I will present is something which is which is a third route based on computing randomized statistics on your collection. So the idea is essentially that you'll choose a number of functions of your data, and you'll build a vector made of the empirical average of each of these functions on all your training collection. So let's just take two examples that are, if your goal was simply to find the average of your data, of course your function would just be take the first coordinate, take the second coordinate, then this would be the average of your data. But that's not really an interesting problem. If you think about PCA, principal component analysis, you know that computing the Gram matrix of the covariance matrix, of your data will capture what is needed to perform PCA. And if you think of each entry of the covariance matrix, well, it's you can write it as a function of your training vectors, and as the average of a function of your training vectors. So you can actually take the vectorized version of your covariance matrix and consider it as a small statistics computed as an average of all your training sets. Well, here where we'll investigate is to what extent this can be done for other tasks than this very simple and well-known task. Can we design so-called sketching techniques to compute moments on your averages on your training data and making sure that these averages are still sufficient for the tasks, the learning tasks that you want to perform. So there are really two parts in this talk. The first part will really be dedicated to what I just mentioned. So in the context where you want to handle large collection, how can you use this compressive learning with random moments? And we'll see that we can do compressive k-means, compressive GMM, and then I'll give a few more ideas on what are the underlying principles. And in the second part, I will also say a word about how to handle large dimensions, in particular in the context where you need to compute linear transforms. And we'll see more about fast linear transforms, what are the characteristics of fast linear transforms, how to learn them, and a few examples. So let's take an example of a moderately large but illustrative collection of data on which you may want to do some learning. And here learning means unsupervised clustering or weakly supervised clustering, because we know we want to cluster it in 10 classes. It's the Mnist data set made of representative from 10 digits. So initially, this collection is made of 70,000 samples in relatively high dimension, a number of pixels, and with 10 classes. The first step is to go in the right feature domain. We use spectral clustering, not spectral clustering, spectral features. So it's a classical technique. So you get now the same number of training samples, but each image is represented by a 10-dimensional vector. And here is a representation of these vectors. When you look at the 5th and 6th coordinates, you can more or less see the clusters. They are actually 10-dimensional vectors. The goal will be to cluster them. What can you do there? The classical way of doing clustering here, k-means, is to run the so-called k-means or Lloyd-Max algorithm, something where you iteratively select centroids, loop through your data to allocate each data point to a centroid, then revise the centroid. So you have to loop to keep your data and do several passes on your data to perform k-means. Here we'll do something quite different. The first step is the sketching step, where we are, from this data, we'll compute a vector, which is the empirical average of some function computed on your data. This function takes your 10-dimensional vector into a 100 or 200-dimensional vector. And so your sketch is a 200-dimensional vector. Once the sketch is computed, you forget the data. So it's sort of privacy aware. There are stronger notions of privacy, but once you have this, you no longer have access to the individual data. You just have access to this aggregated representation of your data. And from this aggregated representation, this sketch vector, dimension 200, there's a technique to learn the centroids. This is essentially based on moment fitting, and I will get back to it. And if you compare to your original data, the clusters, the centroids you learn actually fit the data. So something you can observe here is that the size of the sketch is something which is roughly 100. That's roughly the number of centroids times the dimension, the number of parameters to describe each centroid. So this is essentially the same number of parameters as the number of parameters to describe your the result of learning. You couldn't do with less, otherwise there would be an information bottleneck. But you essentially do in practice with as if you had already computed the centroids, but you didn't need to do Lloyd max explicitly. Do you have any question?
Do you have some examples of some sketch functions?
Yeah, I think I have it, but if not, I will definitely answer your question in a moment. Okay, I can already give a few. Here, the sketch function is actually random Fourier features. So it means that you take your vectors, you multiply them by certain, you take the inner product with certain random vectors, and then you apply the complex exponential or cosines. This is, and I'll get back to it. Yeah. So this was an example of how you can use this aggregation mechanism for compressive learning. So first, you take your data, you aggregate them to a single sketch vector. Second, you estimate your centroids by moment matching, moment fitting. Now, that was for k-means. Now let's look at more audio examples, which is something where we tested on a large-scale speaker verification problem. So it's a proof of concept where what we'll do is we learn the universal background model, Gaussian mixture model, from 1,000 hours of speech. So if you look at 1,000 hours of speech and compute MFCC coefficients, you have 300 million vectors in dimension 12. Now, okay, within these, there's a lot of silence. So if you do a run of silence detection, there still remains 60 million training vectors. And as we wanted to do some comparison with more classical expectation maximization techniques, it turned out that using the VLFit toolbox, the maximum size that we could manage that fit in memory on the machine where it was tested was 300,000 training vectors at a time. So let's see what we can get as a dead curve. So false positive rate, false negative rate for different settings. So here the purple is classical EM, and all other colors represent sketching with different sizes of the sketch. Here you can see that the bigger the sketch, the better the performance. But it never quite reached the performance of EM. However, this is a sketch where we used we've been on par with the number of training samples that EM could use. EM cannot go on this machine with more than 300,000 training samples, but there's no reason why we cannot go beyond, because we can simply do aggregation. The sketching mechanism can be completely distributed, so can be streamed if you have new data. So it's really easy to go to a very large scale. So if we sketch actually with 60 million training samples, the new picture is this one. So what you get is that if you have a small sketch, which is actually smaller than the number of parameters that you need to learn for your GMM, you don't quite match the performance of EM. But with a sketch of size 1,000, so it's enormous compression compared to the gigabytes of data, then you match the performance of EM. And if you do if you compute a slightly bigger sketch, then you're better than the performance of EM. And the whole collection has been, in this case, compressed into something that could fit in a good old floppy disk instead of one of the latest hard drives. Okay, so I hope to have catch a bit of your curiosity on why or how this can work. So I'll just give a quick ideas. So these are ideas that we've developed first in the thesis of Anthony Bourrier, who is now working on completely different things, and in the thesis of Nicolas Keriven, who just defended a month ago in collaboration with Patrick Perez. So the idea is something that came up from the background we had in the team around compressive sensing, and we try to think about what would be the parallel of compressive sensing in the context of machine learning. And here the idea is simply that, okay, when you do machine learning, you have a training set, but you're not really interested in the training set. Somehow there's the issue of generalization. So what really matters is what's the underlying distribution of your data. So think about the object that you're really interested in as the probability distribution of your data. And now, if you say you compute a sketch, so it's the empirical average of some function of your data, well, that's an approximation of the expectation of this function. And if you formally write this expectation like this, you see it's a linear function of your probability distribution. So computing moment is actually something that is nonlinear because this function will be nonlinear. It's nonlinear in the vectors, in the training vectors, but it's linear in their probability distribution. And in signal processing, we're used to manipulating linear inverse problems where we have a low-dimensional vector, which is a linear function of a high-dimensional, here even infinite-dimensional object. But if this object satisfies a certain model, then from this, we have ideas on how to estimate this accurately, and estimating accurately will be a mean of learning the right characteristics. So this is, for those who are familiar with it, this is, it turns out, we discovered afterwards that this is an instance of what is called a min map embedding in machine learning. It's something that takes a distribution and maps it to a kernel, reproducing kernel Hilbert space. Here we do a finite dimensional min map embedding. So we can come back at the picture I already showed once. So in signal processing, we're familiar with the idea that there's a high dimensional object that is observed through a partial observation system. So we have we have a lower dimensional version of this object, and the goal is to reconstruct. Here, what we have is an empirical version of the probability distribution of our data, and through the sketch we have also a linear observation of this. Well, in signal processing, we know that if we want to reconstruct the object, we need a model. We need, for example, to assume that the object is sparse or well approximated by something sparse. And this is well studied in the context of inverse problems. Well, the same type of questions has been studied in the context of statistics. It's called the method of moments. But we can also ask a few more questions. When we characterize settings where reconstruction is possible, we can also wonder, but now can we design this measurement operator, this process, to make sure that this vector is very low dimensional and reconstruction is still possible? So this is the context of compressive sensing, where voluntarily you reduce dimension, and compressive learning, where voluntarily you try to make this as small as possible to have a very compact representation while preserving the ability to retrieve the desired information. So if we get back to our Mnist example, so this is the cloud of points of the data we would like to sketch. So the standard approach would be no sketch, just several passes on the data. It's okay for 70,000 points. It's not okay for 10 trillion points. And here, there's inspiration from compressive sensing, which is, okay, if clustering is going to work, it means that the data is relatively localized in space. In this cloud of points, it is relatively localized around a few spots. So it's spatially localized. And the caricature of a spatially localized set of points is a few Diracs. In compressive sensing, we know that if you have something that is spatially localized, you can sample in the Fourier domain. And sampling in the Fourier domain is something that will capture the information because a sinusoid is completely delocalized. So measuring correlations between something spatially localized and a sinusoid, each frequency measurement gets a bit of information about every place in space. So in statistics or in machine learning, the equivalent of the Fourier transform is the so-called characteristic function of the probability distribution, which means that each entry of the sketch is going to be this empirical average. So this answers your question. What you do is your training vector, you take the inner product with certain frequency vectors, WL, apply the complex exponential here, and average. How to choose the frequency vectors, that's a full topic that is not fully understood yet, but there's a lot of empirical and some recent theoretical work we've done on it to understand how to choose the frequencies. Typically, you need to do a first course pass through your data to have an idea, to calibrate your frequencies, but you don't need to look at all your data. And so with a random choice of frequencies, where you calibrate the variance of, the domain of frequencies that you sample, you can obtain the result that I've shown before. So if you look at in detail, this is also related to the notion of random Fourier features that have been developed popularized by Rémi and Recht. So a Fourier feature is something where you don't take the average. You take just one sample and you do random. You compute. You select these frequencies at random and compute these exponentials. And the vector you get is a random Fourier feature. Here, what we get is we average these random Fourier features over the whole training collection. So these are random Fourier moments rather than random Fourier features. Okay, the question is, okay, how much can you compress? How much can you compress? And to get an empirical idea of what is feasible, we have theoretical reasons to believe that if you have k clusters in dimension d, you should have a sketch vector of size kd. But is it really the case? Well, if you generate random mixtures of k Gaussians to have this type of point clouds, you can test how well the method performs. So where you sketch and you learn and you observe the performance measure, you can compute, well, the cost of k-means, the sums of squared errors. You can compute it with the sketching method. With the centroids computed with the sketching methods. And you can compare it with the same quantity computed with the Lloyd-Max algorithm. So error with the sketching method divided by error that you get if you have access several times to the whole training data. And you can plot this relative error as a function of the sketch size. And what you observe is that whatever the number of training samples, you have essentially the same behavior, which is if the sketch size is too small compared to the number of degrees of freedom, number of clusters times dimension of the clusters, then the performance is not good. But as soon as the sketch size is sufficient, then you essentially reach the performance of the Lloyd-Max algorithm. Okay, I think I'm about to conclude. Now, I'd like to get to conclude this part on sketching. So this is how a sketch is computed. Okay, this is how a sketch is computed from a collection of training samples. Maybe let's try to make it to make the flow, the computational flow, a bit more explicit. So you have a training collection. So these are your training vectors. Now, what does it mean to compute this? Well, first, you see that there's a vector here. You need to compute the inner product with such a vector. So this here is the vector. If you compute the inner product between this and all these vectors, you get one big row. And if you do it with the matrix that contains all these vectors, you actually multiply your data by some matrix W, and you get something which is, in fact, thicker. Now, you apply a nonlinearity, which is the complex exponential. And finally, you average everything. So this should be reminiscent of some familiar architecture. This is known, in fact, this is a one-layer neural network with a pooling, with an average pooling. If you think that these are the frames of an audio signal, if you take these training signals as the frame of an audio signal, then you've used the same matrix for each frame, so it's a convolutional filter. Then you've applied the nonlinearity, and then you average pool. So your sketch is the output of one layer of a convolutional nets. So what essentially we've demonstrated, and we have some theory about it, is that there's some information preservation guarantees when you want to infer characteristics of the distribution of your data, for example, Gaussian mixture models or clustering. Now, an interesting property of this is that once you've computed the sketch, as I already said, you don't need to access the data anymore. The sketch has captured the information for the task that is being performed. So there's a sort of privacy, and I believe there's more to be said in the future on privacy preservation with this, because you could even do noisy computations in a way to add noise on each training sample, while making sure that in the end the sketch is almost the same, but revealing almost no information on each training sample. In terms of computational framework, it's also useful to see that if you have new data coming in, it's really trivial to update a sketch. So in a streaming scenario, there's no problem with updating the sketch as data flows in. And also, in another context where you have devices that are distributed all over the world, each can compute its sketch, and you can combine the sketches from the different devices, which makes it possible to compute, let's say, a universal background model for data that you have never centralized anywhere, with just the sketches. So I hope to have convinced you that okay, there's a sketching framework with nice computational and potential for privacy. That's on some examples showing that it can be quite memory efficient, and while preserving the desired information, as displayed by these empirical success curves. We have released a toolbox to apply to test the framework on certain the mixture modeling learning tasks. There's a theory also for the information preservation of this scheme. What is the main challenge from a theoretical perspective today is to understand whether the empirical algorithm that we use to learn from a sketch actually have provable performance guarantees and can be made more scalable. How much time do I have? Okay, I'll do something quick on now. I propose to do something quick on this idea of fast linear transform, which deals with the complementary perspective on this large-scale learning. Instead of simply compressing the number of trainings along the number of training samples, we want to handle the fact that we have high-dimensional vectors and matrices. So this is the result of the work of the thesis of Luc Lemagouarou. The idea is, okay, linear transforms, you find them everywhere, but so the cost of applying them when it's a large matrix is important, both in terms of storing the matrix, but also in terms of computing multiplication by A or A transpose. And also, if you want to learn such a matrix from pairs YX, then you need a lot of training samples to estimate m times n parameters. So, when possible, people like to use fast transforms. Fast Fourier transform, wavelet transform. See, these are fast. So, do you know why these transforms are fast? Any idea? What's the fundamental reason why such transforms are fast? Okay, I'll give you a hint. It's because this transform, the matrices associated to this transform can be written as the product of a few sparse matrices. Think of the FFT. The FFT is fast because you have the butterfly algorithm for the FFT, and the butterfly algorithm, it's log n layers, where on each layer you have few connections. You have some permutations and few multiplications. So it's really a product of log n sparse matrices. So here, don't worry about the exact structure but gray is zero coefficients, and the rest is non-zero coefficients. So the Hadamard transform here, which this is the matrix associated to the Hadamard transform, it's a product of a few sparse matrices. So the idea is that, well, any fast linear transform is fast because it has this type of structure. So if you are given a matrix, if you want to approximate it by something fast, well, then try to approximate as a product of few sparse factors. The advantage is that this structure covers all existing fast transforms, but also if you have something, I mean, it can be adapted. It's more flexible than existing fast transforms. Then you get speed benefits. You also get storage benefits, and you get improved statistical significance because there are fewer coefficients to learn when trying to fit such a model. So the principle is you're given a matrix, you try to find an approximation of this type. We formulate it as a non-convex optimization problem and propose an algorithm. So I'm not going to give much detail, but it's an algorithm. If you run it like this, try to figure immediately all the factors, it doesn't work well. We propose an initialization strategy that recursively factors into two sparse factors and then factors. So it's a hierarchical factorization process. And putting all together, you get a number of examples that only develop one or two. This one is we reverse engineered the Hadamard transform. So the Hadamard transform, we know it's a matrix that is the product of a few sparse matrices and harmonic analysis. I mean, the theory tells us this. Existing implementation exploit that. What we did is we actually took the dense matrix, ran the empirical algorithm, and we got an exact factorization of the Hadamard transform. It's not the same as the original one, but it's an exact factorization with the same number and with the same sparsity, so with the same cost from every perspective. Second example, take a matrix that's associated to a BCI, brain-computer interface problem for EEG source localization. And there are two ways we can approximate this matrix, either with the SVD or with these approximate fast transforms. Here, we display so one would be a dense matrix, approximation with a dense matrix, and here this is the number of non-zero coefficients in the product of sparse coefficients. And for the SVD, the equivalent would be the number associated to the rank of the SVD that you compute. So we get a different regime of compression for this type of matrix. So DCL speeds up, and when you use this approximate matrix for source localization, we get the same performance. So this is also to show the actual runtime with if you use the dense version of the Hadamard matrix or its approximation, and this is the speed. So the speed up factor you get by using the factorized version rather than the dense version. Okay, so let me conclude. So I hope to have convinced you that when you face large-scale learning and you have constraints on your resources, well, in terms of the size of the collection, something you can, sketching and compressive learning can be a tool, at least in the tasks that I've mentioned. We know k-means, Gaussian mixture modeling, principal component analysis. Some of the things we're looking at are, okay, to what extent can we use this framework for other learning tasks? And when you have to handle the high dimension, fast linear transforms are also, we already have a number of settings where we've demonstrated their potential. In particular, most recently, we've published something on graph signal processing. We have a fast graph Fourier transform, which is computed with this type of techniques. And on this, I'd like to thank all the collaborators with whom this work has been conducted. Thank you.